Alright, hello everybody. Good evening. Hope you enjoyed your holidays. We're back to work, and then next week we're on holidays again. So we're kind of oscillating back and forth between holidays, and it's the 10th of Tevet next week. So we're gonna be off. Which means once again you have 2 weeks here of homework. You have a nice long time, which means you can do it extra well, and I can give you extra hard homework because you have the extra time. So we can all enjoy ourselves. For today, we're going to, this is the second part of the harmonic oscillator. We're going to meet an alternative way of dealing with it. We call the ladder operators, raising and lowering operators. I'm sure you've seen them in class, A and A dagger. So we're going to introduce them, show how they work, how to work with them. We're going to solve a very instructive example to show why these ladder operators are so useful and why they come in handy. And then we'll talk about something called coherent states, which you'll also meet again in your homework. Also a nice bit of physics behind there. Questions before we start? All right, let's go ahead. So I'll remind you, when I introduce the raising and lowering operators, so I would like to remind you first of all of the Hamiltonian that we're dealing with. So it's quadratic in both the momentum and in position. Now if, right, this is, what I'm going to write down next is wrong, but if P and X were not operators, then we could write, and you can verify this quite simply, so I'm gonna write it like this, minus I P operator, and then N. So you see that when I multiply these, actually 4 terms when you multiply this by this, but 2 of them cancel, because there's a minus here and a plus here. And the remaining 2 terms are this p squared and this x squared. But this is only true, right? This is wrong. This is wrong, and why is this wrong? Because they are operators, and the order between x and p matters. So actually what is true is that the multiplication of these 2 brackets if I multiply the first bracket by the second bracket, what we actually get is m squared omega squared x operator squared, right? That's this times this. Then the second one times the second one is the p squared. And then the remaining 2 terms actually do not cancel. What you get is xp minus px. So that's why I'm saying that if they were not operators, then p times x and x times p would be the same, and this bracket would be 0. But since these are operators, and the order matters, this minus this is not 0. Actually, you saw in your homework a couple of weeks ago that if you, this operation actually gives you IH bar. You solved that weeks ago in your homework for the example of a plane wave, but it's true in general. Just take it as a fact for now. We're going to, in the next tutorial in 2 weeks, we're actually going to see that this thing is actually called a commutator and where it all comes from. But you've shown this for the plane wave. I'm telling you it is true in all cases, in all of quantum mechanics, that xp minus px is IH bar. In the classical limit, when h bar goes to 0, it's exactly what we know. They're C numbers are classical numbers, and this will be 0. So a classical limit is when h bar is this goes to 0. Will be a classical limit. Now, what this means is that I can actually replace this bracket times this bracket. So this is wrong, right? So the correct way of factoring the Hamiltonian would be by writing 1 over 2m m omega x minus ip. Then the second bracket with the plus sign. But then I need to add what was taken off. Which, as you can see here, is h bar omega divided by 2. I've already factored out the 2m as well. Okay, so the I times the I gives a minus sign. So it's negative here, which means I have to add it in order to get rid of it, right? And if I then divide by 2m, I'm left with exactly h bar omega divided by 2. Now notice that this is precisely the ground state energy. So the additional term is the ground state energy. And remember that the ground state energy is a direct consequence of the uncertainty principle. And here we see that it comes from the fact that the order of the operators matter. And there is a deep connection, which we'll also uncover more in following weeks, between the fact that operators are not invertible and between the uncertainty principle. That's actually one and the same thing. So it has the same, that's the origin of this term, and that's why it's the ground state energy. That's why in the classical case, the ground state energy is a 0, because that wouldn't exist. Let's manipulate this a little bit further. I would like to work with dimensionless variables. What I'm going to do is I'm going to multiply the entire Hamiltonian by 1 in funny way of writing 1. I'm going to multiply the entire Hamiltonian by m omega h bar divided by m omega h bar. And that way, we obtain the following. So the first bracket is root m omega over h bar. You can go over the calculations at home, make sure I'm doing correct. It's always a good exercise to check. And then we get the same thing again with the plus sign. Plus the ground state energy. So I multiply top and bottom by this. Once it's outside, second time it's inside, but then I have to well, it's inside once here and once here. So there's 1 over root m omega h bar here, or 1 over root omega h bar here. If you multiply both by each other, you can actually say what I actually did is I multiplied it by root m omega h bar times root m omega h bar. This is what I actually put in. So put the first root into the first bracket, the second root into the second bracket, and the denominator is outside. Okay, it's a little bit technical, but you'll see where I'm going with this in just a second. Maybe you see it right away already. Remember that we defined a typical length scale in position and in momentum space. This thing here is none other than 1 over sigma x. This thing here, without the I, so this is 1 over sigma p. You might remember this from last week, from 2 weeks ago, which means we can now write this in a much simpler way. I'm also going to cancel the m, so I have h bar omega divided by 2. Then there's an x operator divided by sigma x minus I p operator divided by sigma p. And then the same thing with the plus sign. Plus the ground state energy. Now you see that all these terms inside the brackets are dimensionless. X operator has dimensions of a meter, right? It's a length divided by the typical length scale of the problem. It's momentum divided by the typical momentum of the problem. So all of these things are dimensionless. Right, all of them, this one, all dimensionless, and all of the units are actually contained outside. You know that h per omega is an energy. It's Hamiltonian, it must be an energy. So I've taken out all of the dimensions to the beginning, so now it's very easy to read like this. That's where I was going. Now, we're in a place where we can define the raising and lowering operator. Why they are called raising and lowering, we'll see in a second. But notice that the first bracket and the second bracket are simply the complex conjugate of each other. So I will define something we call a raising operator. That'll be the x operator divided by root 2 sigma x minus I p operator divided by root 2 sigma p. This is raising. And I'm defining something I call the A operator, which is the same thing with a plus sign. I've defined new operators, but you shouldn't be scared of them because you know exactly what they are. You know what the x operator is. You know what the momentum operator is. So now you just take this minus that, and that's a new operator. So there's no reason to become scared of this or to not like this. It's just a combination of other operators. Now you will notice that these, before we go there, with this definition, the Hamiltonian takes a really simple form. So it's A dagger A plus 1/2, where the units are outside, h bar omega. So from now on, this is our Hamiltonian operator. So it takes a very simple form. This symbol that we put on top of the A is called a dagger. And it means take the Hermitian conjugate. So you see that the raising operator is the Hermitian conjugate of the lowering operator. This is a little different than the regular operators that we've met up till now, because most of our operators were Hermitian, right? So we know that, for instance, the Hermitian conjugate of the position operator is the same thing as the position operator. That's why it's called an Hermitian operator. The Hermitian operator, by definition, is an operator which is equal to its own Hermitian conjugate. The same goes for the momentum operator. And we said there's a postulate, we talked about this a couple of weeks ago, that only Hermitian operators, so only operators where this is true, that it's equal to its own Hermitian conjugate, only such operators can be physical observables. But A is not equal to A dagger, which means that the raising and low operators cannot be associated with a physical observable. You cannot measure A or A dagger. Because they're not equal to each other. Okay, is this clear? This is a very important point. Taking an Hermitian conjugate basically means taking, if you want to take the Hermitian conjugate of an operator, which is a sum of operators, it means you have to take the Hermitian conjugate of each term individually. And so you take the Hermitian conjugate of the x, you're left with x. You take the Hermitian conjugate of p, you're left with p. A Hermitian conjugate also means that you have to take the complex conjugate. So the I turns to minus I, so you see right away that this is true. Hermitian conjugate means take Hermitian conjugate of all operators plus take complex conjugate. So you turn I to minus I. Question about this?
I did not understand why we need this operator, because we know the formula of the energy in a harmonic oscillator.
We'll see in a bit why it comes in handy. You don't need it because, yes, you have another formulation, but you will see that this formulation makes a lot of calculations much easier. And we'll get there in a moment. For now, it just looks good. It's much easier to write this than that.
Yeah, but and you show us that the energy is F plus N, H bar omega. So why we can't use that? Why we need this?
Well, that's good. That is still going to be true. Just because you change your formalism and you're using different operators, the physics will not change. So the energy spectrum will be exactly the same. You will see in a moment why this makes it obvious. Okay? This is also an harmonic oscillator. Okay, so we said that neither the A or the A dagger correspond to physical observables, of course not Hermitian, but if you look at the product of the two, this thing is Hermitian. So the Hermitian conjugate of this is equal to itself, and we call this the number operator. The number operator, we define it, it's an operator, n op is A dagger times A. It is equal to its own complex conjugate, so it can be associated with an observable. Another thing you have to know about these operators are why they are called raising and lowering operators. So for phi n, this is a harmonic oscillator eigenstate. Okay, then acting with A dagger on phi n will give you root of n plus 1 times phi n plus 1 x. And if you act with A, on phi n of x, you'll get root n phi n minus 1 of x. So this is probably the most important formula of this lecture, this tutorial. It's a raising operator. So when a dagger acts on an eigenstate, on the nth eigenstate, with energy h power n plus 1/2, then what you will get is a higher energy state, higher by 1 n, n plus 1, up to some constant which has to do with normalization. And the same thing for the lowering operator. You act with a on phi n, you get an energy state, an energy eigenstate with lower energy, n minus 1. So it's a raising operator and a lowering operator in energy space. This also shows you that the phi n's are not eigenstates of a and a dagger, because when you act with a dagger on phi n, you do not get phi n, you get a different function. So this shows you that phi n are not eigenstates of a and a dagger. Okay? So for an exercise, for example, find the action of the number operator on phi n of x. Probably guess what it does because it's called a number operator. It's called that for a reason. Let's just see how simple this is how simple these rules are to use. So I'm acting with the n operator on phi n of x, which basically means I'm acting with a dagger times a on phi n of x. So first of all, right, order matters, right? I need to be careful what I do with the order. So which one acts first? The a, right? The one which is closest to it. So I can keep a dagger where it is. Now when a acts on phi n, so you see this formula, I get root n times phi n minus 1. Okay? Now root n is just a number, so it doesn't matter whether I first multiply and then act with a dagger or first act and then multiply by a number, it's just a number. So this is actually the same as root n times a dagger times phi n minus 1. And now when I act with a dagger on n minus 1, right, so I need to use this formula, but with n minus 1. So I just get root n. So root n times root n times phi n of x, which is equal to n times phi n of x. Summary, the number operator acting on phi n is equal to the n, right, the number, that's called the number operator, times phi n of x. So you see that the phi n's are eigenstates of the product. They're not eigenstates of the individual operators, but they are eigenstates of the product. Now guess what? This product appears in the Hamiltonian. And that should answer your question. When the h operator, Hamiltonian, acts on phi n of x, and we have h power omega a dagger a plus 1/2, which acts on phi n of x. So h power omega is just a number. A dagger a takes out n. Half is just 1/2. And we have found the energy spectrum, the energy eigenvalues. In a much simpler way than we did last time. So we know exactly how the operators work. So this form of the Hamiltonian makes this makes this apparent, makes this clear. Questions so far?
Is it only relevant to the harmonic, to this specific Hamiltonian?
Yes.
And what do we do if we have a different Hamiltonian?
And you solve the problem. If you have an infimotential well, then you solve the infimotential well. This is harmonic oscillator. A and A dagger are defined for the harmonic oscillator. Different problem, different solution. It's not surprising. One more thing. The way we defined A and A dagger, we can also invert the definition and express the position, a momentum operator, as a superposition, or the sum or difference of A and A dagger. So you see that the X and the P operator are either A dagger plus A or A dagger minus A. I just got this by taking the definition of A dagger and A in terms of X and P, and then eliminated X and P. That's what I did. Okay, let's introduce something called the bracket notation. I'm going to introduce the bracket notation specifically for the harmonic oscillator today, because it's useful, it's simple to read. We're now starting to do with real quantum mechanics. In 2 weeks, the next tutorial, we'll use the bracket notation in a more general form for the entire realm of quantum mechanics. But for today, it's going to be just for harmonic oscillator. So let's just agree to write. It's an agreement between you and me and the rest of the world. We write this symbol. It's an N, straight line, then a triangle. And what we mean is the harmonic oscillator eigenstate, phi n of x. When we write it the other way around, what we mean is the complex conjugate. This thing is called a ket. This thing is called a bra. Together it's a bracket without a C. You get the point? This is just an agreement, right? We can make this agreement. There's nothing to it. It is now much easier to write the way A and A dagger act on the eigenstates. We can now just write that A dagger is root n plus 1 times the n plus 1 state, and this is root n minus 1. The strength and the good thing about this notation is that I do no longer have to write phi n of x or phi n of p. I don't care whether it's x or p, because A and A dagger don't care about x or p. All they care about is whether it's n or n minus 1 or 7 or 5. So that's the only thing that matters. That's why this bracket notation is so strong and very easy to use, and because it's very handy for this kind of problem. I only care about which state I'm in. I don't care what was in presentation I'm working. Actually, this is the energy basis, because these are energy eigenfunctions, right? So when A dagger acts on the nth state, I get the n plus 1 state. That's all I care about. No need to write x or p. So it comes in handy. For instance, I can now write that when the Hamiltonian acts on the nth state, that's h bar omega A dagger A plus 1/2 acting on the nth state. So I know how A dagger A acts on the end state. It takes out this n. So I don't really care whether I'm working in X representation or B representation. I don't care where my derivatives are and where I multiply and anything of that. I don't care about Gaussians or Hermites or anything. All I care about is that I'm in the end state. I don't even have to think about who are my polynomials and all that sort of stuff. I don't care about it anymore. So all you guys who are starting hating those polynomials in the fun homework I gave you, you see you don't even need it. So I've been torturing you for nothing. Obviously not for nothing. You know how to work with both tools, and it's important to understand how the eigenfunctions look like in X space and P space. Obviously, there's a lot of physics behind that as well. But you see that for many calculations, there is no need to go there. Calculations can be simplified a lot. Questions? Okay, now using this new notation, the notation that we have been using for expectation values becomes obvious. Remember, we have been writing that the x, for instance, the average of x is the integral of phi n star of x times phi n of x dx. Or sometimes we have been writing that is the integral on phi n tilde star of p IH bar ddp phi n tilde of p dp. Right, this is the same. This is X representation, this is P representation. You realize this is just the same as saying n X operator n. I've introduced this notation before. You now understand where it's coming from. This n is phi n, that's this. This n, right, the bra, is the star, that's this. Now, obviously, this is also equal to, I didn't note it here, but this is also equal to phi n tilde of p. Right, because this notation does not care about X or P space. I can work on whatever space I want. That's what this means. This is equal to each other. Obviously, the average of X does not depend on which basis I work in. This is the notation. So it makes much more sense, and it's much easier to use.
It doesn't really matter, but isn't there a minus in the IH bar DODP?
I don't think so, but I could be wrong. I think that the P operator in X space has a minus, and the X operator in P space does not. But I could be wrong. That's what we have cheat sheets for, formula tables, because no one remembers these things. Okay, let's solve an example to see why it is, to implement how to use this notation. We would like to compute the expression A dagger A minus A dagger acting on n. So if the order is irrelevant, this will be 0. We will see that the order is relevant. It doesn't matter whether you act A dagger A or A dagger. So it depends if you could think, but it doesn't matter. Who cares if I raise and then lower, or first lower and then raise? I'll end up at the same point. So it turns out you don't. And we'll see in a second, but this is what this means. Okay?
Didn't you say this is the number operator?
Excuse me?
Didn't you say it is the number operator?
This is the number operator.
No.
Sorry, this is the number operator. This you might think is, but as we'll see, it's not. Because the order matters.
It's almost.
We will show it in a second. If we find that this equals 0, then this will also be a number operator. Well, it's not. So just solve it and then we'll see.
I'm just confused because the number operator we said is Hermitian. And it's kind of looks
Right.
like what you would think would be the...
Hermitian conjugate? It's not. No.
It's not.
let's take the Hermitian conjugate of the number operator. Okay, it's obviously no, because it's not equal to itself, right? So we say the number operator is A dagger A, right? I want to take the dagger of this, right? So how do you take a Hermitian conjugate of a product? I haven't told you this yet, but I'll tell you now. You have to do two things. One, you have to change the order. Two, you have to take the dagger of each. So take Hermitian conjugate of each operator. So what you get is, you first switch the order, okay? So I'm going to write this one first, A operator, and then I have to take its Hermitian conjugate, and then I'll write the first one as the second. Okay, so I switch the order, I'm taking the Hermitian conjugate of each individual one. And now the Hermitian conjugate of A is just, it's A dagger, these brackets are meaningless. And the Hermitian conjugate of the Hermitian conjugate is just A itself. So now you see that this is equal to N. So this is equal to itself. It is different than this. Okay? It's an important point.
When you're changing the order, you don't transpose?
Well, if it were a matrix, how do you transpose?
Yeah.
Yes. So in matrix, we'll talk about it in 2 weeks, in the next tutorial. The Hermitian conjugate, you should have learned this actually first year. A Hermitian matrix, right, is equal to the compass conjugate and transpose of itself. It should be something you know. If you don't, then work on your linear algebra. It's going to be important.
Yeah, we didn't learn that if you change the order, it's like transpose. We see it in a single matrix.
Okay, so that's for a product of operators or matrices. Okay, let's get back to the example. So we want to compute this. It's quite simple. It was already pointed out that this is just a number operator. So this part is simple. Just gives the number. But the second part, we now have to act first with A dagger. So when we act with A dagger on N, here's our formula, we get root of N plus 1. We can then move this in front of the operator and act with A on N plus 1. So we use this formula with N plus 1. And what we get is N plus 1 times N. So if I do this minus this, I find it's equal to 1 times N. Right? The N cancels.
Minus, right? Minus doesn't.
There's a minus sign here, right? What happened? Yeah, there's a minus sign here. Now let's do it like this. I switched the daggers, okay? So I've added the minus sign here, basically. Sorry for that. It doesn't matter, but this is a more a typical way of writing it. So what we have, I'll write the conclusion, is A dagger minus A dagger A equals 1. Or A dagger equals 1 plus A dagger A. So you see that this thing which is not the number operator is actually 1 plus the number operator. So it matters if you lower first or raise first. That's basically my point. Questions about this? Right, very good. It's time for our example. Excuse me? It's an identity operator, yeah. Which is multiplication by 1 if it's function or a diagonal. We're not doing matrices yet. Don't think about matrices. That's next week or 2 weeks. Don't think about them yet. I promise you we'll get there. I noticed that you guys love linear algebra, so I've already put a homework up with 4 pages of linear algebra, so I'm sure you're going to enjoy it. Yeah, no, they regret it for saying it. Linear algebra is very important for quantum mechanics, but we'll deal with it with all its importance in 2 weeks. So for the moment, it's just multiplication by 1. Okay. All right, let's solve an exercise. As promised, we're going to calculate moments.
Isn't it the -1 if you wrote the A before the A dagger?
Well, we just did that properly now, didn't we?
Yes, it's supposed to be a minus.
He changed
It's the
it.
-1.
No, I thought we had it proper. I thought we corrected it now.
Yes.
A dagger will give n plus 1. And A dagger A will give n. So n plus 1 minus n is 1. Right? It's wrong on the paper. That was the comment 12 minutes ago. But my notes are wrong. There are always mistakes in my notes. Don't trust them. Okay, so we'd like to calculate moments. Let me tell you the problem. We would like to find the average position and the second moment of the position as a function of time for a particle in a harmonic well, described initially by psi naught of x, which is a superposition of phi 1 of x plus phi 2 of x plus phi 3 of x. It's a typical problem, which, by the way, you know how to solve. You've done this for similar questions in your homework. You know how to write phi 1, phi 2, and phi 3 as Gaussians and Hermite polynomials. You know how to write x, and you know how to integrate. This is something that you know how to solve. You've done it. But you will now see that using the line operators, the calculation becomes much, much simpler. And that's why we have these operators. So we can work hard 1 week, and then the next week we can become Pazamnikim and do it properly. So, okay, is the question clear? Simple question, right? How do we solve it? So first of all, let's write this in bracket notation. So now we have that psi 0. I'm not writing psi 0 of x anymore. It's just psi 0. I mean this thing, but I don't care anymore if it's in x space or in p space or any other space you may want to invent. This is equal to 1 over root 3, 1 plus 2 plus 3. So state 1 plus state 2 plus state 3. I've eliminated the position from the problem. Okay? Now let's evolve this in time, which means we want to find psi of x and t, or better, just psi of t. Who cares about x, right? So it's just the ket, but the ket, of course, can depend on time. And because we are already working in the energy eigenbasis, you know exactly how to add a time dependence. Each eigenstate receives a phase of e to the IE divided by h bar t, where the energy is E1, E2, and E3, right? According to the Schrodinger equation. So we find psi of t is 1 over root 3. I'm going to factorize out a factor of 1/2 before everything. You see in a second why this is so nice. And I'm missing a cat over here. Right, so the cat psi of t is a function of time. So here I added e to the 3 halves, right? Because it's 1. So n plus half or n equals 1 is 3 halves. So there's 1 here and a half here. So that's 3 halves. And then 5 halves and 7 halves. Right? So 1 and a half, 2 and a half, and 3 and a half. But the 1 half I took outside. I factor it out. That way I have to have every single time, which is writing once at the beginning. Okay, this step is clear? So what I did from here to here is solving Schrodinger's equation. But because I'm so used to Schrodinger's equation, and because I'm working in the energy eigenbasis, it's very simple to evolve the wave function in time. Now, what has to be done? We would like to, let's start with the mean position. So the first moment of x. So what we want to calculate, I'll give you in a second, is this. Yes, question.
Why didn't you consider the ground state?
It's given. This is given. Phi 1 plus phi 2 plus phi 3. That's the question.
Yeah, but phi 1 does not need to be phi 0.
No, it's a given initial condition. It could be phi 0 plus phi 5. It could be phi 77 plus, whatever you want. It's a given initial condition. I chose it because I don't know what, and that's what I'm working with.
So
there's no reason.
I omega is depend level.
Yeah, this is because what I skipped a line here. What should be written here, right, is 1 over root 3, and then there's e to the minus I e1 over h bar t 1 plus, and then there's an e2 and then e3, right? And e1 is 1.5 h bar omega. So the h bar cancels, and I took half outside, and I got here. I just skipped a line. Sorry for that. Should have done it more carefully. Is it clear now? Okay, so all we want to do is calculate the average. So this is the formula, right? We need an active psi of t on both sides. So we need to know what all of these 3 terms are. This term we already know. The ket. That's this. Right? Now the second term, the first term, the bra psi of t, that's the Hermitian conjugate of that thing. So what we have to do is take the complex conjugate and switch all of the kets into bras. So we get e to the plus I omega over 2t. Right? That's the complex conjugate of this part. And then there's an e to the plus I omega t. And then there's a bra 1 instead of the ket. And the same for the second term. And for the third term. So that's that. And the third term is the X operator. But since we're already working in the basis of 1, 2, and 3, so in the energy eigenstate, we're going to express the X operator in terms of A and A dagger. That's what this lesson is all about, obviously. And that way the calculations will be much simpler. Okay, everything clear so far? We know what we have to calculate, and we have all of our ingredients. Let's put it all together. This is x of t, right? So x of t equals, so we have this times this, first this times this, then times this. So first of all, notice that when I multiply this e to the minus omega divided by 2t by this, they just cancel. That's why I took them out. I knew they would cancel. And then the root 3 times the root 3 is just a third. And I'll take this number out to the beginning as well. So what we'll get is third, and then it's going to be a square root h bar over 2m omega. And then I have all of this mess. So there's an e to the I omega t 1 plus e to the I 2 omega t bra 2 plus e to the I 3 omega t bra 3. And then I multiply this by a dagger plus a. And then this, then I close with the ket, which is this thing. So it's e to the minus I omega t 1 plus e to the minus 2 omega t 2 plus e to the minus I 3 omega t 3. There we go. It's a long expression, but you'll notice in a second that it is really simple to calculate. If we were not working with a dagger, you would now start integrating like crazy, right? Which you did. I hope you did. But it's not much easier. Before you start, think, right? This is what we have to do. If we would open up all the brackets, right? We have here 3 terms, here another 2, here another 3. If we open up just all the brackets without thinking, we'd have 18 terms. So you can be my guest in writing them down if you want to, but I wouldn't. What you should remember is the way A and A dagger act on these 1, 2, and 3 states. So what we have to use is the fact that A dagger acting on 1 gives root 2 times 2. A dagger acting on 2 is root 3 times 3. A dagger acting on 3 is root 4 times 4. That's easy. A acting on 1 is just 0. It's the ground state. There's no negative numbers, right? And starts with 0. A acting on 2 is 1. Root 1 times 1, but that's just 1. And when it acts on 3, we get root 2 times 2. Root 3, sorry. Sorry, I'm wrong. This is root 2 here. Here's a root 1, which is 1, and then there's a root 2 times 1, and a root 3. That means, all right, so let's just use these relations and just multiply this by these terms. What we get are 6 terms. We get the following 6 terms. So I'll just write down again the first half. Now this is multiplied by. Right, so let's first of all act with a dagger on these 3 terms. So we get e to the minus I omega t, and then there's a root 2 times 2. That's a dagger acting on 1. That's this times this. And when a acts on 1, we get 0. There's plus 0 here. The next term is e to the minus I 2 omega t. Now when A dagger acts on 2, we get root 3 times 3. Are you following me? And when A acts on the cat 2, we use this equation right here, we get root 2 times 1. And we'll do the same for the third term. So we get root 4 times 4 plus root 3 times 2. This is the point in your homework where you should hold your page's landscape. Now, why is this so useful, right? It's get to the point already. So, we use orthogonality which means that when this gra multiplies this term, we get 0. If we multiply this term, we get 0. When we multiply this term, we get 0. When we multiply this term, we just get 1, so that survives, and 0 and 0. Next, let's take this term. We multiply by this, we get a non-zero contribution. This is 0, 0, 0, 0, and here we get another one. Okay, everybody following? And one more, I'm out of colors. 3, 3. So out of the total 18 terms that we could have written down, only 4 of them survive. So what we get, right, after we put it all together, is a third root h bar over 2m omega. That's just this constant from the beginning. Now when 1 multiplies 1, we get root 2 times e to the I omega t. Right? And when this 2 multiplies this 2, we get root 2 times e to the minus I omega t. So we have root 2 e to the I omega t plus e to the minus I omega t. That's 2 terms already. Right? That's this term and this term. And then there's 2 more. They both give a root 3. Right? But this time we get e to the 3, e to the, there's a 3 up here, right? And then this exponent is a minus 2. So we're also left with just I omega t. Right? So there's a root 3 times e to the I omega t minus e to the minus I omega t. Everybody see that? Okay, I'm just looking at the different terms, taking them together, and there we are. That's all our terms. That was easy. Now this, of course, is twice the cosine. It can be factored out. So we find our solution. It's 2/3 root h bar over 2m omega. It's just sigma x over root 2. I don't know why I'm writing this way. Then there's a root 2 plus root 3. It's just a number. Not a very nice number, but it's just a number. Times cosine omega t. There we are. That's the solution. Excuse me?
Why did we get the minus?
I didn't. I'm just writing too fast. Sorry. There's a plus sign here. That's why they're both a cosine. I factor it out. I'm left with the root 2 plus root 3. And there's a cosine. And the 2 is because it is twice the cosine. That's it. I hope you're not surprised that the average position is a cosine. Because quantum mechanics on average is classical, right? And the classical motion of an harmonic oscillator is a cosine. Or a sine, whatever. That's not surprising. Questions about this? Okay, let's move on to, well, it's 7 o'clock already. Let's move on to x squared. So what we want to calculate next is the second moment as a function of time. So we have to calculate the psi of t, x squared psi of t. We know our bra psi, we know our ket psi of t, and the x operator squared, we know that as well. It's this thing squared, but of course when we take the square of the sum of operators, we again have to watch out for the order. It's not twice product, but it's once this times this plus once this times this.
And we know the permutation relation.
You do. We're going to use it in a bit. You still have to watch out for it. So we get A operator dagger plus A operator dagger, A operator. There you go. So we have all of the ingredients. It's now just a matter of writing it all out and looking at which terms cancel and which do not. So after cancelling the overall phase of the 1/2 inside and taking out everything to the front, so there's a 1/3. Where are we? Okay, there's a 1/3, and then there's an h bar over 2m omega, and then there's a psi, there's e to the I omega t 1 plus e to the I 2 omega t 2 plus e to the I 3 omega t. 3, this is very repetitive. Then this is multiplied by a dagger squared plus a squared plus a dagger plus a dagger a. And then there's the ket closing the expression with the minuses in the exponent. Now again, before we start, think. There are 4, or let's split into 3 terms actually. There are 3 parts. There's this part, call that 1. There's this part, call that 2. And then there's this part, let's call that 3. So when So what happens is that when a dagger squared acts on the nth eigenstate, you get something that is proportional to n plus 2, because you're raising twice. So the only term that can survive with a dagger in the middle is if the term on the right is 2 times higher than the term on the left. That means that the only term that survives is the one, sorry, other way around. It's the one with the 3 on the left and the 1 on the right. Right? Everything else cannot possibly exist. This will just be equal to root 6, I think. Where am I? Yeah, that's just root 6. And later on, we'll also have to take into account all the phases. So this is number 1. number 3, we can use the same trick. When A acts on n, we get something that's proportional to n minus 2. So the only term that can survive is the one with the 3 on the right. It gets lower twice, we'll left that 1, and then the orthogonality gives us 1, otherwise it will vanish, and this also equals root 6. And from the third term, when A dagger plus A dagger A, it's not the same as before. Beforehand we had a minus sign in the previous example. There was a plus sign. So instead of getting n plus 1 minus n, we'll get n plus 1 plus n. Right? So when that operator, when A dagger plus A dagger A acts on the nth state, what you get is 2n plus 1 times the nth state. So if you close that with m, on the left-hand side, what you'll get is 2n plus 1 delta nm. So the only terms that will survive the third operation are the ones where the left and the right are equal. So either 1 with 1, 2 with 2, or 3 with 3. Everything else.
You know that's 2n plus 1? I didn't catch this part.
Beforehand, we did the exercise A dagger minus A dagger A, and we say it was n plus 1 minus n. There is a plus sign, so it's obviously n plus 1 plus n. But you can go through the calculation. You can go through the calculation using the relations, and you'll see right away. It's not that difficult. Just trying to get to the coherent states as well at some point. So the 3 terms that contribute, right, are the terms that are, we get 3 terms. There's the 1, 1. There's something in the middle, right? So there are a total of 5 terms. Take down all the phases, put them in the right place. What you'll get is 1/3 h bar over 2m omega. This is the root 6, and then there's going to be an e to the I2 omega t plus e to the minus I2 omega t. That's what survives when you multiply the third by the first state. This times this, you're left with e to the minus 2 omega t, right? And you get 1 from the first and 1 from the second operator. And then from these 3 terms, they have the same phase, so no phase will survive. The only thing that will survive is the 2n plus 1. So you get plus 3, plus 5, plus 7. Right, that's 2n plus 1 for n equals 1, for n equals 2, and for n equals 3. Really simple. Of course, if you prefer to solve Gaussian integrals, be my guest. Just group this all together. We get h bar over 6m omega. 15 plus 2 times root 6 cosine 2 omega t. There we go. That's the second moment. Once again, we did not even think about the location, the position, the momentum, anything like that. All we have to work with is the way A and A dagger act on the nth eigenstate. That's all we have to know. Questions about this?
I just didn't catch how did you do square root of 6?
I acted with A twice on A twice on 3. So doing steps, you'll get 1 times A, and now A acts on 3, right? So A acts on 3, that'll give you root 3 on 2, right? And now so there's root 3 upstairs, there's 1 here, and now A acts on 2. And that'll give you root 2 times 1. Now this with this just gives 1, and root 2 times root 3 is root 6.
Ah, okay.
like I said, that's all I'm using. All I'm using are the relations of A and A dagger and how they act on the eigenstates. That's all I've been using for the past half hour. It's very powerful, and I recommend you get used to it, and you'll see that you will get used to it, especially after you solve the homework, because there are a lot of exercises. Okay. Obviously, from here, if you wanted, you could also calculate the uncertainty. You have x squared, you have x. You could calculate even the time dependence of the uncertainty, and if you wanted, you could verify that this is always larger than h bar over 2. Be my guest at doing that. Okay, questions? Okay, last topic for today. 20 minutes will do just fine. Great. So I would like to talk to you about something we call coherent states. I will define them, show you what that means, what a coherent state is. I will not explain why it's called a coherent state, it's just a name for now. You'll understand the name coherent state in about 2 years, okay? So it's really confusing why it's called coherent state. Doesn't matter, okay? But it's a nice exercise to solve for it. And it helps understand the formulas of quantum mechanics in a very nice way, which is why I'd like to introduce them now, although their physical explanation will only be understood in whoever stays in physics in a couple of years. Whoever doesn't stay in physics will have to miss out forever. So I'm trying to keep you in physics. Okay, definition. Take the A operator, okay? I'm acting on some state which I'll call alpha, and that equals to the number alpha times the state alpha. This is an eigenvalue equation. This is obviously an eigenstate. This alpha here is the eigenvalue. This is the eigenstate again. How do I know it's an eigenvalue equation? Because that's what it does. It's an operator acting on a state, returning a number times the state. But now because A is not an Hermitian operator, alpha is not a real number. Alpha can be complex. It's an element of the complex group. Alpha is complex. Simply.
So coherent states are the...
So coherent state is by definition an eigenstate of the long-ring operator. Coherent state equals eigenstate of lowering operator.
What the eigenvalue will be always equal the eigenstate?
Yeah, it's like before we had n, right? We had the nth. It's the alpha state.
Yeah, but it shouldn't be alpha minus 1.
No, it's not the nth state. It's something else. It's not an harmonic oscillator eigenstate. It's an important point. This is not an harmonic oscillator eigenstate because when A acts on the harmonic oscillator eigenstate, you don't get back n. It's not eigenstate.
It's okay.
These are the eigenstates of A. We said that the n are not. These are. Two different things. Okay? So we said coherent states are the eigenstates of the lowering operator. That's a definition. If you want, of course, you can write the A operator in the X representation, for instance, and then solve this differential equation and find alpha in X space. I do not recommend it. It's nearly unsolvable. But you can just work in this bracket notation and everyone understands what you mean. Right? That's why I like this example, because it really implements the formalism. An important thing I'd like to stress is that these are not the eigenstates of A dagger. Okay? What is true is that the bra alpha and then A dagger up is equal to alpha times the complete conjugate of alpha. This is true. And this is true. But if I would add a dagger here, that would not be true. And you can check this right away, because you take the Hermitian conjugate on both sides. Remember, you have to switch the order, and then take the Hermitian conjugate of each single one. So if you take the Hermitian conjugate on both sides of this equation, you'll get this equation. In order to get from here to here, just take the Hermitian conjugate. Is that clear? Now, the coherent states are normalized. We're always free to make this choice, obviously. If we would solve the equation in any space, we would have an integration constant, which we could use in order to normalize. So we're always free to make the choice that they're normalized. So let's make it. It'll make our life simpler. So alpha times alpha equals 1. But they are not mutually orthogonal. They are not orthogonal. The bases spanned by the set of all alphas is what we call overcomplete. What does that mean? Overcomplete means that any vector, any state can be written as a superposition of the alphas, but there is more than one way to do so. It is like spanning three-dimensional space with four vectors. So I would have x, y, and z, and some additional vector pointing in some random direction. If I have four vectors in two-dimensional space, I could express some random vector in different ways, different combinations. That's what overcomplete means.
How do you know it?
You're going to prove it in your homework. Not joking. You actually are. Overcomplete. So any state can be spanned by alpha, the set alpha, but there is more than one way doing so. What your question actually should be is, how do I know they're not orthogonal? Because if I know they're not orthogonal, then it's obvious that I can, that I have maybe not enough. In this case, more than enough vectors. The fact that they're not orthogonal, you're going to calculate in your homework. You're actually going to calculate the inner product between alpha and beta, so some other coherent state.
For every state of function, we have more than one way to describe it using the alpha states?
Pretty sure, yes. It might be a counterexample, which I'm not thinking of. I'm pretty sure and even the alpha itself can be spanned by different alphas because they're orthogonal, right? It's an overcomplete basis. I'm guessing yes, but I'm not sure. It might be some really weird combination that only exists once. Could be. I'm not sure. Okay, let's have an example with the coherent states.
That means they are linear independent.
Excuse me?
That means that they are linear dependent.
Yeah, they're linear dependent. Okay, example. So we're considering a particle in a coherent state. It's given that it's prepared in a coherent state, right? Particle in a harmonic oscillator, obviously, is prepared in the coherent state alpha 0. So alpha 0 is a number. It's a complex number. And it's 1 plus I, or 1 plus I, because it's normalized. But it's some complex number. So it could be 1 plus I. I don't need the product to be normalized. Some complex number, which I'm going to call alpha 0. So there's a particle. I have a machine that spits out particles in coherent states. Such machines actually do exist. I'm not inventing this. Okay. It's called a laser. That was really confusing, so forget about it. Okay. But okay, this exists. Find the expectation values x and p. So we're looking for the average position and the average momentum of a particle in a coherent state. It's a fair question, right? Okay, so let's do so. Average x, by definition, is closing the x operator with the Brown-Eket of that state, right? Now I can write the x operator as a sum of a dagger and a. Right? We know that. Nothing new. Now let's write the two terms here. So let's write out the terms. So the first term is the sandwich of a dagger. And the second term is the bracket with a. Now I can use the definition of the coherent states. When A acts on alpha, I get alpha times alpha. So when A acts on alpha 0, I get alpha 0 times alpha 0. Right? And now when this A0 is closed with this A0, I get 1, because they're normalized. On this side, I cannot act with a dagger onto the ket. That's not defined. What I can do is act backwards onto the bra. Sounds funny. Okay? See what I did? I'm acting backwards onto the bra instead of forwards onto the ket. And then, of course, once again, the A0 and the A0, the bra and the ket are normalized, so we get 1. So we find h bar over 2m omega square root alpha star plus alpha, or alpha naught star plus alpha naught. So this is the sum of a number and its complex conjugate. That's just twice the real part, right? So this is equal to root 2h bar over m omega times the real part of alpha 0. Okay?
Why root 2? It's actually supposed to be 2, no?
So there's root 2 on the denominator? So what's the problem?
Twice the real part of
Yeah, and there is a root 2 in the denominator.
Right.
It cancels. This, by the way, is just root 2 times sigma x. Right. Okay, let's do the same for the average momentum. Am I overgoing time? You guys got somewhere to be? Work for your homework? Yeah, about 5 minutes. I'm fine. No?
He said 5 minutes.
Oh, you said 5 minutes. Okay. So, average P, by definition, acting with alpha on both sides of the P operator. The P operator is now written in terms of A dagger and A. And now use the same trick as beforehand. This A can act on here. This A dagger can act backwards onto the bra. So we get I root m omega h bar over 2 alpha 0 star minus alpha 0. This is a complex conjugate minus itself. So this is minus 2i times the imaginary part of alpha 0. Right? If it's hard for you to see these relations, just try to write it out. Say that alpha 0 is x plus iy, and this is x minus iy, and you'll see what you're left with is just the y, so the imaginary part. It's really simple to check these relations. So in the end, what we get here is root 2m omega h bar times the imaginary part of alpha 0, which is just equal to root 2 times sigma p times the imaginary part of alpha 0. And I'm coming to an end. You see that the average position is related to the real part of alpha. The average momentum is related to the imaginary part of alpha. That means that alpha 0, right, this number that defines the coherent state is 1 over root 2 sigma x times x, the x average, plus I over root 2 sigma p times the p average. So the mean of alpha, right, it basically incorporates the average position and the average momentum. Just say one more sentence. Coherent states are sometimes called quasi-classical states, or almost classical states. And this relation makes that clear, because they're related to the average values of momentum position. Not the probability or anything like that. The average momentum, which is classical, and the average position, add them in some weird complex way, you get this number, that's coherent state. So coherent state is quasi-classical. If you didn't so interested in the end, that's fine. Just wanted to have it out there. So when you hear it in 2 years' time again, you'll say, now I understand. Okay, questions? All right, so, your vacation.